I'm going to give a talk today that actually started coming out of a graduate seminar I taught in occupancy modeling with a bunch of graduate students back at University of Connecticut. And so I want to start by actually acknowledging the two graduate students or former graduate students who are the co-authors on this paper with me, Chris Nadeau, who's now a Smith Fellow working at Northeastern University, and Minette Sandor, who is now a Frontiers of Science Fellow at Columbia University. We're talking today about community size and how we can estimate community size, because of course imperfect detection affects our estimates of community size because we're going to miss things, not just at the site level, but also at the region level. And so we can think of essentially the number of species that actually exist at a site as being composed of three different kind of classes. The first is actually the species that we identify at the site in this sort of green box at the bottom. The second is the species that are not detected at a site, but are detected at other sites. So we essentially know their identity and that they may exist at the site we survey. But there's a third block too, which is the species that are not detected, not just at the current site, but at any sites, but essentially do exactly or actually exist in the region. And so these different sort of classes of species sort of tell us different things, and we have different ways of estimating them. Normally through study design, we might actually try and shift species from from the white pool into the yellow pool by adding more sites to our study. We also might try and shift species from the yellow pool into the green pool by adding more surveys. What I'm talking today about is actually sort of a way to try and get at these number of species that are in this white pool by using sort of estimates to get at regional community size or gamma diversity. People have been using occupancy models in a variety of ways to look at community ecology for a number of years. This is a paper by Lance McNew and Connie Handel in 2015 that uses multi-species occupancy models to look at whether or not we can estimate the true alpha richness of species at sites. More recently, our very own chair, Guru, published a paper with colleagues in ecology and evolution that again was using multi-species occupancy models to calculate alpha diversity. That is the number of species that actually exist at a site. Of course, diversity exists across many different scales, and one of those scales is essentially the regional diversity or gamma diversity. And that's what I was particularly interested in is working with, is trying to figure out whether or not we can use multi-species occupancy models to estimate gamma diversity. This is done primarily through a technique called data augmentation. Data augmentation in occupancy models goes back to Andy Royal and Bob D'Orazio, who modified essentially your standard multi-species occupancy model by saying that the true probability of occurrence at a site, that's Z, is a Bernoulli function, not of the probability of occupancy, but that multiplied by this indicator variable W. W itself is a Bernoulli random variable of a parameter omega, where omega is being multiplied by essentially the sum of the number of species that actually we know occurred across all of the sites that we surveyed in our study, plus some arbitrary large number of augmented all zero capture histories. And so we can use this data augmentation to essentially estimate omega, and through omega, get an idea of how many species actually occurred at all of our sites in our region, that is to say gamma diversity, that may have not been seen at any of our surveys. Now, of course, you don't have to use multi-species occupancy models to get this. There are a variety of other types of alternatives to get gamma diversity. Probably the current other sort of main one right now is using the iChow2 estimate, which is a non-parametric estimator. iChow2 is sort of a more recent modification of the previous Chow2 estimator that uses the incidence frequency counts at sites. That is to say, how many species occurred at only one survey, or only two surveys, or only three surveys, et cetera, to get at this estimate of how many species may have not been found at any surveys. That is to say, Q0. And so iChow2, of course, is a very common and widespread and relatively easy way at estimating species richness and gamma diversity in particular. So my study focused on two main questions. The first is, well, in general, how good are multi-species occupancy models at estimating this true community size or gamma diversity? And secondly, how do multi-species occupancy model estimates compare to non-parametric estimators, in particular the iChow2 estimator? We wanted to use this, test these two questions using two approaches. The first, of course, is using simulation to look at how sensitive these things are to a variety of different conditions, then ideally test them in the wild with empirical data. So the simulation, we came up with a lot of different scenarios. So first off, we decided that we were going to simulate two scenarios of survey sites, a system where we only had 30 sites to survey and another where we had 60 sites. We also came up with two different true community sizes, one where the true community size or gamma diversity is 20 species, and the other was 125. We then chose two different types of number of replicate surveys per site, 2 versus 7, and then 7 different scenarios of detection and occupancy probabilities. These 7 different scenarios kind of ranged across what we thought might be essentially the average occupancy probability and average detection probability of all species within the community. We also then changed the variation in those average hyperparameters. So our 7 different communities then change in terms of essentially the ideal scenario where you have high average occupancy, high average detection, and relatively low uncertainty in both of those, or variation from species to species, I should say, to essentially community type 6 and 7, which are these unideal scenarios where you have low occupancy, low detection, and generally high variation in both of those as well. So we have these different combinations of survey site, community size, replicate numbers, and then scenarios of detection and occupancy hyperparameters. For each of these, which is 56, we took 100 replicate data sets for each of these combinations, modeled the simulated data using multi-species occupancy models and iChow2 estimators, calculated the estimated true community size, compared it to that truth. We then evaluated that as a function of 4 different evaluation criteria: bias, precision, accuracy, and coverage. The data looks something like this, where we have our 4 different ways of evaluation: bias, precision, accuracy, and coverage probability. We have our light gray bars for the iChow2 estimates and our dark gray bars for our multi-species occupancy model estimates. And you can see going along the x-axis that numbers 1 through 7 refer to those scenarios from essentially ideal to unideal. And then with various ways of calculating, well, how many reps did we have versus like 2 versus 7, et cetera. So what are some salient features? One is that all these green arrows are pointing to scenarios 3, 6, and 7. And you can see that essentially across bias, precision, and accuracy, you're getting these higher bars for scenarios 3, 6, and 7. Those are all the scenarios where you had low average occupancy. So low average occupancy, regardless of iChow2 versus multi-species occupancy models, it leads to higher bias, lower precision, and lower accuracy. Scenarios 6 and 7, which have low average occupancy and low average probability of detection, generally also do worse. Not surprising. These are the unideal scenarios, so we expected them to not do great. In general, in terms of bias, multi-species occupancy models tended to be biased high, so they overestimated the true number of species in the community, whereas iChow2 estimates sort of varied. Sometimes they were biased high and sometimes they were biased low. We generally expect them to be biased low because iChow2 is generally referred to as a lower bound estimator. So if anything, they're supposed to be underestimating the true community size. In general, multi-species occupancy models provided very good coverage. In fact, our estimates pretty much always got 100% coverage probability. The iChow2 estimates had lower coverage probability, meaning the confidence intervals did not overlap the true community size about 20% of the time for iChow2. We then did a separate simulation where we actually varied the occupancy probability from 0.1 to 0.9 across this sliding scale to look at the sensitivity of low occupancy on its own to this bias, precision, and accuracy problem. In general, we found relatively similar patterns that once you get around a mean occupancy probability across all species of less than around 0.2 or 0.3, that's when you start to see large increases in bias, precision, and lower accuracy. So that's the simulation. The second part was actually testing this in the wild with our empirical data. And for this, we used a long-term time series data I work with primarily of looking at bird communities in post-fire forests in California. For this, we actually monitor birds in 50 different fires each year. Across those 50 fires, we surveyed about 400 point counts. We've been doing this for over 9 years of data, and this we only use 9 years. And across those 9 years, we basically plateaued in terms of the number of species we see. So in total, we've seen 123 species across this area, but only about 88 species per year. The question, because we've essentially seen this plateau in our species richness, the question we want to ask is, can we estimate the true community size with just 1 year's worth of data? So instead of going out for 9 or 10 years, can we actually estimate the true gamma diversity with just 1 year of the data? And so we use those individual years as replicates, and this is a box plot of the estimates from each of those 9 years, either for the naive data using iChow2 or for multi-species occupancy models. And so you can see, of course, that the iChow2 and multi-species occupancy models get much closer to the true community size of 123 species compared to the observed single year estimates of the community size. If we break that down by actual year, you can see that the multi-species occupancy models in the iChow2 estimates end up actually sort of diverging a fair amount. So if we just look at coverage, we can see that, for instance, the 95% credible intervals, which are the thin bars, actually cover, they get to the true community size in all 9 years. You don't have that same coverage probability with the iChow2, for instance, in year 2010, 2016, in 2018, it does not actually reach that true community size. In many cases, the multi-species occupancy model, 50% credible interval is even overlapping with the true estimate of 123 species. If we look at actual performance metrics, we can see what we just talked about here, that the reason perhaps the multi-species occupancy models have greater coverage is because they have greater standard error in their estimates. And so if you just look at the average standard error of that estimate of community size, the multi-species occupancy model is about twice as large as iChow2. At the same time, if you look across all of the 9 estimates across those years, the multi-species occupancy models had greater precision, and they also had about much greater accuracy as well. The final thing we looked at is just within the multi-species occupancy models, we wanted to look at how they were biased by these sort of hyperparameters of mean probability of occupancy and mean probability of detection. Each of these dots is a posterior sample, and you can see essentially then they're colored by their year. Basically, what you want to look at on the right is that no matter the mean probability of detection for the different years, it didn't affect our estimates of the community size of the, but on the left side panel, what happens is that when the model, basically when it starts to think that there's really, really low mean probability of occupancy, then it starts to skew really high and you have these exponential increases in the estimates of true community size. So that leads us to our conclusions. The first is that non-parametric estimators such as iChow2 are really surprisingly good for their simplicity. So I'm not trying to say you shouldn't use them. I think they're fantastic. But if you're worried or curious about these multi-species occupancy models, they actually do a really good job using data augmentation and estimating gamma diversity, and probably better than iChow2. At the same time, low average occupancy across all species and community is a real danger for estimation. This is controllable via study design, such as spatial scale, but it's something to watch out for depending on how you've actually designed your study and the data you have. So with that, this paper has been published in Methods of Ecology and Evolution, funding, contact, and I think I have time for one question.